Awesome, let's get started now. Okay, so I'm going to be talking about big data mining infrastructure. Let me begin by telling you a little bit more about myself. So my name is Jimmy Lin. I'm actually associate professor at the University of Maryland over in the States in the DC area. From 2010 to 2012, I had the great fortune of doing a sabbatical at Twitter. And so this is what I like to say to people. I came out of the ivory tower of academia and onto the factory floor, where I spent a couple of years building shit that works. Okay. All right, so before we get into this any further, just a disclaimer. So this is my personal opinion, doesn't represent the view of management. Void where prohibited, your mileage may vary. And, oh. Yeah, you're gonna let me talk about this. I can see my slides perfectly fine, but yeah, do you wanna all come up here and we can huddle around? Okay. You don't see my pretty pictures. Okay, I have to do it again, but then I've lost my thunder already because I've given away the punchline, so. Yeah, okay, rewind. Okay, yeah, I'll just show you the pretty pictures. So, as I like to say, coming out of the ivory tower onto the factory floor, building shit that works, and I've worked basically as a software engineer for 2 years at Twitter. Okay, so in my humble opinion, this is my personal opinion, doesn't represent the viewpoint of management, your mileage may vary, and if anybody asks, I probably wasn't here, although since this is being recorded, I've lost my plausible deniability here. Okay. All right, so let me start off with sort of an abstract view of what the Twitter architecture looks like. So on the front end, they're the front end hosts. These are all the web hosts that serves the as the front end boxes. There are a whole bunch of scribe hosts that do the logging. I'll talk about that in a little bit. Over there on the side here, you have the MySQL database. You store the graphs there, and the tweets get stored there. In the center, and this is somewhat an analytics-centric view, is our Hadoop cluster, right? So all the data gets loaded into the Hadoop cluster. There's some real-time aggregation stuff on the side, but I won't talk about that. And so on the back end, we basically do 3 things. We do a lot of dashboarding, we do a lot of ad hoc analyses, and there's also a whole bunch of data products that get pushed out to the front end. And really the star of the show is this guy here, Pig. And so most of the analytics is done using Pig. Okay, so let me just sort of give you a sense of scale of how it was and how it is today. So yesterday, this is when I first joined Twitter in the middle of 2010, and there were about 150 people in the entire company as a whole. There were about 60 Hadoop nodes, and actually the funny thing is, when I got there, we actually had a Hadoop outage for quite a while, which is inconceivable today. Typically, there were on 6 people that use the analytics stack on a daily basis. And so we're just getting started back then, basically. Now, fast forward a couple of years. Today, the entire company has about 1,400 people. About half of them are engineers. We run tens of thousands of Hadoop nodes across multiple data centers with an aggregate capacity tens of petabytes across those data centers. We ingest about 100 terabytes daily, and dozens of teams, so instead of 6 people, dozens of teams now use Hadoop on a daily basis. And collectively, they submit about tens of thousands of Hadoop jobs on a daily basis. Okay, so I think this is preaching the choir. I mean, why do we invest so much in this infrastructure? I mean, this is preaching the choir here. Everybody knows the formula, right? So we turn data, we have data, and we want to turn it into actionable insights on the one hand and data products on the other hand, right? Okay, so big data mining, right? People ask me what I do at Twitter, and one of the things I do there was big data mining. And so the usual response I get is, well, cool, you get to work on cool algorithms. And in fact, I sort of look at them and say, oh, how misguided. No, not really. Right? And so the biggest thing I've really learned in the last couple years is that big data mining really isn't about data mining per se. And that's sort of one of the key messages I want to share with you. All right, so many of you probably know DJ Patel. He wrote this awesome book a little while ago called Data Jiu-Jitsu. And so his quote, and I think is mostly true, is about 80% of the work in any data science project, data project, et cetera, is all about the data cleaning. Right? So here's a reality of things, right? And when you're embarking on a data science or data power projects, Your boss comes to you and says something vague like, our core metrics, we got to improve them. And then you sort of shrug and say, what do you want me to do? Right? And then you sort of think very hard about how to move the needle. And you're like, OK, I have an idea. So I need some data to play with it, to try out my experiments on, right? And so the first question, well, where's this data, right? OK, 5 email exchanges later, you finally get access to the data. And then you're like, start poking at the data. What's in this data set? And you poke at it for a while and said, what is all this bleep, 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 bleep stuff in the data? Because as it turns out, you're the first one to look at it. And it's got a lot of, shall we say, unexpected abnormalities in it. OK, right? So you spend a lot of time cleaning the data. And then, then really is the data mining aspect of it. You run some off-the-shelf algorithm, topic modeling, k-means clustering, you train some classifiers, et cetera. But comparatively, that's not much of the task. Right? So you do this for a little bit, and then you finally productionize the whatever product or whatever insight that you get, and you act on it, right? All right, and then you go back, since this is an iterative cycle, you rinse and repeat. Right, so this box that I've drawn here is really the data cleaning side of things, right? I mean, this is what DJ Patel says takes up 80% of the time. And so the message here is that, data science is a little bit less glamorous than what everybody thinks, because you do spend all that time on data cleaning and data munging. OK, and so my job over the last couple years has been this. How do we make data scientists' lives a little bit easier? And that really is the main purpose of my talk today, is that we want to share with you some of our experiences. So on this path to building a scale-out big data mining platform, let me tell you, it's a long and winding journey. There are a lot of bumps in the road. Sometimes you end up driving on the wrong side of the road. And the goal of this talk is to, by sharing some of these experiences with you, for those of you that are coming down the road after us, you'll have an easier time. OK? All right. So the focus of my talk primarily today is going to be on log data, right? Because that's probably where the bulk of the data lie. Right, so we're talking about application logs, service logs, interaction logs, your click-throughs, your impressions, things like that. Right? Tweets are 140 characters, right? Even if you have hundreds of millions of them per day, that's not going to add up that much. This is where all your data is. Right? So I'm going to be talking about tips and tricks for gathering data, for moving data around into the data warehouse, and then for organizing. I hope you enjoyed these images, because it took me a long time to find them. OK, all right, so let's start off with the first brilliant idea somebody always has. They're like, brilliant idea number 1, let's log directly into the database. Right, the rationale here is, well, in the open source world, you're probably running something like MySQL anyways, right? Hey, so why don't we just log into the database? You create a table that looks something like this, and then, you stream your log messages there. OK? Sure, good idea, right? No, you don't want to do this. And you don't want to do this for a variety of reasons. Right? First of all, there's a tremendous workload mismatch. Right? On one hand, you need logging. This is large streaming writes. And it's going to interfere with your other load, which are going to be primarily scan-based, involving much smaller amounts of data. Right? So that's number 1. Number 2 is scaling challenges. Right? You want to be successful. And if you're going to be successful, you're going to have to scale up your infrastructure. Right? Scaling up sharded MySQL, it's doable, but it's certainly hard. You don't want to be scaling that up and your log infrastructure at the same time. Right? It's also overkill. Right? So logging into a database provides you some type of consistency guarantees that are just too strong for things like impression logs and click-through logs. Okay? And then finally, what are you going to do when your schema changes? Right? So if I recall correctly, when you change a schema MySQL, you have to lock the entire table, right? Which means that you basically have to freeze the world to have a schema change. Right? You typically get around that by setting up a generic sort of like key value structure, but that sort of defeats the whole point of having schemas to begin with, right? OK, so don't do this. What you want to do instead is something like Scribe, and Scribe is actually what Twitter uses. And so Scribe is a log transport mechanism that was open sourced by Facebook a few years ago, and the architecture looks something like this. So in our main data center, we have a whole bunch of production hosts, and all of them have Scribe daemons on them. The scribe daemons forwards the log messages into what are these known as the scribe aggregators, who basically roll up the scribe messages. And this is where we do some ETL. So we do compression, some sanity checking, build indexes, et cetera. And all of these data get put onto what we call a staging Hadoop cluster. Okay, and then periodically, we do a bulk copy from these Hadoop staging clusters into the main data warehouse. And this pattern is replicated on a per data center basis, right? So you have this sort of structure in another data center and a third data center. Okay, so at Twitter, we decided to standardize on Scribe, but certainly newer systems such as Flume or Kafka, LinkedIn's Kafka distributed queuing system is a viable alternative as well, right? So don't log into a database, use something like Scribe or Flume or Kafka. Okay. So we've solved the log transport problem, right? So Scribe solves a problem physically moving the messages around. The next issue is, what is it that we should actually log? Well, the first idea should be obvious, right? We're going to have like system.out.println or your log.info, so let's just log that. Okay, that's not a good idea. Because I can tell you, plain text log messages suck. And here's exhibit A. So I had to pull this out of Git, but this was an actual Java regular expression used to parse logs. Mercifully, this has been retired. Okay, but can you imagine trying to maintain this? Okay, so don't do this. Don't log in plain text. All right, sort of as an aside here, here's also another interesting problem. And the basic problem revolves around this. Naming things is hard. Okay, so how do you name things? Well, you can use camel case, and these are your old school like Perl hackers, right? You can name things in small camel case. This is like your Java hackers, right? You can have things in snake case. These are C++ hackers, right? And sometimes you get them mixed up, and you end up with a camel snake. Or you get mixed up even more, and you end up with the infamous dunder snake. And this is real. Here's a tweet to prove it. Actual instances of the camel snake and the dunder snake in the code base. Okay, so what's the practical effect of this? Well, the practical effect of this is, look, what is it? I want the user ID. Is it UID? Is it user ID? Is it lowercase user, capital ID? And all these possible variants. Okay, so naming things is hard. All right, let's talk about the next brilliant idea. And that's it. JSON to the rescue. Right? Isn't that the sort of the next logical evolution step? Okay, so here's a sample JSON message. And I'm here to tell you, based on our experience, this does not scale. All right, so this might work for a small, rapidly iterating development team, but this just does not scale. Let us recount the ways in which a message like this can go bad. Right? So remember the camel snake. Right? So what happens in separate code paths, you use different naming conventions. So half the messages are user ID, the other half are user underscore ID, and you lose half your messages. Right? Let's take a look at this. So this is the user ID. It's like a screen name, right? So usually it's like a string, but this particular user just happens to want numeric digits as his or her screen name, right? Seems totally legit. Well, you know, some upstream process saw this and said, oh, hey, it's an integer, when it should be a string, and it casts it as an integer. Okay, now you got a type mismatch. Down the road, when you try to do joins, it blows up in your face. Okay, what about this? So, you know, you're doing A/B testing, pushing out, trying new features, and yeah, this really should have been a list, right? We forgot to engineer that. So, okay, we'll fix it tomorrow, but for a bit, just to sort of get around and push the product out, let's stick like a comma-separated string in here. Okay, right? And then, you know, the delimiter doesn't get documented anywhere, and so the people that come after don't know what's going on. Or even worse, tomorrow does happen, and yes, this does get fixed into a string. And now, half your messages are this comma-separated string monstrosity, and the other are actual list, right? And so you have all these branching code paths in your analysis script that says, you know, if it was generated before, do this. If it was generated after that time, do that. This is not sustainable, right? Okay, This is one of my favorite one. How do you express null in JSON? Is it a null string? Is it an empty string? Is it nil? And finally, here's another one I like. So this is an embedded complex object, right? So what are the keys? What are the values? Right? So what ends up happening is you go ask the front-end guy that wrote the code, and he was like, I don't know. I wrote that like 3 months ago. Go look at the code yourself. Right? So you go in and end up looking at code. Or better yet, I have fond memories of doing this. You write pig scripts that crawl through a few terabytes of data, building histograms of key value distributions to figure out what's there. Okay. How many of you have run into these issues before? Raise your hand. Okay, for the record, almost everybody raised their hands. Okay, this is not a sustainable way to do data science. This does not scale. Okay, so what should we do? Well, the answer is we got to use something like Thrift. We got to use something that actually imposes a schema via like a data definition language. Okay, so what are the advantages of using something like this? Well, the DDL provides type safety, right? It provides auto-cogen in whatever language you want to read, write, and manipulate these structures. It also allows you to do efficient serialization, right? So you're getting rid of all the integer.parseInts in your code. Right? It also gives you a sane path to schema migration via adding optional fields, right? And then finally, it separates the logical from the physical. And once you do that, you can start doing things like playing with different compression techniques, playing with column organizations, and all that fun stuff. Right? So as long as your underlying physical storage layer materializes the data in the expected format according to the DDL, you're fine. Right? So there's tons of advantages there. Right? So Thrift is certainly an option, but if you don't like Thrift, protocol buffers is another viable alternative, or something like Avro. These are all equally good. It's just that historically at Twitter we happen to settle on using Thrift. Okay, all right. Next idea. So schemas alone aren't enough. What you actually need is a complete data discovery service. Right? So you want to have the ability to answer these questions, like, where's my data? How do I read it? Who produces it? Who consumes it? And when was it last generated, et cetera. Right? Provenance. This is what we need. And let me illustrate by telling you yet another sort of series of stories with respect to pig. Okay. So the question is, how do you find where data reside? Right? So the old way we loaded data looks something like this. Right? You have a load statement in pig. The problem here is that the path is hard-coded, and it has a hard-coded partitioning scheme. Right? So it's YYYY, MM, DD, HH. Right? And you have to know that it happens to be LZO compressed. Right? You also need to know the custom loader, a particular loader that is designed to load and deserialize that type. Okay, so how do you find this out? How do you discover what data you need? Well, there are two ways. The first is to ask around. And if you're a small team, this works. Hey, Dimitri, I need to work on this type of data. Where is it stored, and how do I load? Okay, so that's number one. Number two is you cargo cult. So let me tell you, find dot dash name star dot pig, pipe it to xargs grep is a very powerful tool. Right? So we have this joke inside that internal at Twitter that there is one pig script that is the source of all pig scripts, and every other pig script is simply a copy and paste mutation of it. Right? You don't want to do this. You don't want to train data scientists to be cargo cult programmers. All right. Okay, so the new way, we've tried to make it better, and here's how we try to make it better. So the new way of loading data looks something like this. Instead of giving them a complex path, we give them something that has a more logical organization. There's the same loader every time, and the loader knows via metadata how to access it. The filters are now pushed down into the loader, so the engineer doesn't need to know the specific partitioning scheme. Okay, right? And then we provide a nice UI for browsing the data sources available. Okay, So how do we do this? This is work that we're still work in progress. This is things that we're still working on. But we introduced something called the data access layer. And the idea of data access layer is nicely illustrated by this quote. So you know, all problems in computer science can be solved by an extra layer of indirection, right? Except for that problem of having too many layers of indirection. Okay, so this is how the data access layer works. So we basically route all data accesses through the DAL, and then you know the DAL is essentially just a thin layer on top of hcatalog, which is a generalization of Hive's metastore. So as I like to say, it's turtles all the way down. Okay, but once you have something like the data access layer, which tells you, you know, who wrote the data, when, and what data, you can do all sorts of cool things. And this is still work in progress. But for example, you can automatically construct the data and job dependency graph. Right? So you have all your upstream sources that get imported. You have at the end all the data products that come out. And in this middle, you have this huge pachinko machine, right, of data flows that are dozens of layers deep and you know, hundreds of jobs wide. You can automatically reconstruct that. Right? And from that, you can automatically figure out ownership. And then if you're clever about it and hook it into your alerting system, your auditing system, your repos, and your deploy systems, you can do cool things like, hey, you know, I noticed that this job was running slower than usual. You know, when was the last time the system was deployed? Let's go into the repo, get blame to see what lines were changed, and automatically email the engineer responsible for that. Right? This is all enabled by the DAL once you provide all the nice hooks to it. Okay. So that's sort of the first section of my talk. I want to move on next to talk about plumbing. And this is work that a colleague and I published in Sigma last year. So what do I mean by plumbing? By plumbing, I mean how to get disparate systems to work together in a cooperative and nice way. All right, let me illustrate. I'll illustrate specifically with the problem of classification. Okay, so let me just run through the classification problem. But intuitively, everybody in this room has experience with it. Classification is a machine learning problem of sorting things into bins. Right? So you start off with a feature vector, a collection feature of vectors in the labels. In the spam classification example, this is, you know, here's the email message. Is it spam or is it not spam? You know, 0 or 1 is the label. Right? So you have a whole bunch of these training data. I'll denote by the red circles and the green circles associated with the features. And then in machine learning, there's two stages, right? There's the training stage and the prediction stage. Right? So in the training stage, you're going to run all your data through the learner, and you're going to learn a classifier. Right? The method by which you learn is typically by minimizing the loss. So it's a function induction problem where you want to find the parameters that minimizes a loss. Okay, so that's on the training end. Once you get the classifier, you simply put in new feature vectors with unknown labels, and you get out, you know, is this a red one or is this a green one? Okay, so let me describe what we were doing before, what I call sort of the Stone Age in machine learning. Okay, so we start off with data in HDFS, and by this time, it's all nicely organized because, you know, you've done all the things right, like I talked about in the first session, right? Okay, so you do pig to do the data munging, you join together multiple data sets, you extract features, etc. And then you downsample. And you downsample so that it fits onto a single machine in the data center. And then you build a model. Right? So you train the model, and then you download new data, the test data, and then you make your predictions, and you copy the data back out. And sometimes you do this, most of the time you do this on another computer in the data center, but sometimes you're doing this on your laptop. Okay, what's the problem with this? Well, there are two serious issues, right? We're talking about big data, right? But downsampling so that it fits onto a single processor defeats the whole point of big data to begin with. Right? So that's the first big problem. And the second problem is that how are you going to productionize this? You're going to productionize this in a very ad hoc way, and it's going to be disconnected from the rest of your workflows. Right? So what ended up happening is we had a lot of one-off processes that were running on cron. So there were lots of cron scripts that periodically, you know, copy the data over, train the model, copy the data back, etc. Right? And this is not manageable. This is not scalable. Or even worse yet, we had something that I called a human cron, which requires an engineer to periodically remember to update the model. It's like, yeah, just remember like every week to retrain and update the model. Okay, are there any human crons in the room? No? You're too shy to say. Okay, all right. But so this is what I mean when I talk about plumbing. I mean, the plumbing is these production considerations, right? So the dependency management, what are the upstream processes that are generating your data? When do you schedule your processes? Resource allocation, monitoring, filtering, error reporting, alerting, things like that. Okay, all right. So we really need to have two criteria. Number one is we need to have seamless scaling. Right, so we need a system that can scale on megabytes of data on a laptop to terabytes of data in the data center. Right? So that's criterion number one. And the second is that you have to have integration of the production workflows. You have to get the plumbing right. Okay? All right, so the way that we actually end up doing this is using a strategy called stochastic gradient descent. Now, without getting into all the math here, the intuition is really, really quite simple. So the intuition here is that conceptually, we want to turn classifier training into a user-defined aggregate. Okay, I bet everybody in the room is already familiar with the most famous user-defined aggregate. That's average. Right, so user-defined aggregate, when you define it, has three phases. Right, you have an initialization phase, you have an update phase, and you have a final termination phase, right? So in the initialization phase for average, you have a sum counter, and then you have a count counter, and you set them both to 0, right? In the update phase, you add to the term and you increment the count, and at the end, you return the sum divided by the count, and you get the average, right? Okay, so wiping away all the fancy math, machine learning training, a classifier, is exactly the same idea. With stochastic gradient descent, you have initialization phase where you initialize the weights. Right? In the update phase, this is where the math is, right? But it's just hidden in this path. I mean, what you're doing here is you're updating the weight vector in accordance with the gradient with respect to the loss function. But honestly, that's math. That's just a lot of floating point operations. But the intuition is still there. You're updating the weights. And then in the end, you return the weights, and the weights define the model parameters. Okay, so that really is the insight. Using stochastic gradient descent, you can fold classifier training into something that looks like a user-defined aggregate. Okay, and so the next stage is how do we put that into Pig? Well, so you have all the previous Pig workflows. Right, so this is feature extraction, joining the data sets from disparate sources, et cetera. And when you get to the final end, when you get to a reducer, what you simply do is you run it through a Pig storage function, and you have the learner that's embedded in it. Right, so a Pig storage function is an abstraction of how to serialize data, right? Usually it takes a tuple and then writes it to UDFs or something like that. Right, so what we do here is we take the learner and then stick it in there. The learner accepts the input tuples and interprets them as the label and the feature vector. And then once the model is updated, chucks it away. And at the very end, it writes out the model parameters. Right? So we take the learner and essentially fold it into the storage function. Right? So you do whatever you were doing with Pig before, then you say store, and that does the training. Okay, you might look at this and say, well, you only have one reducer. Doesn't that cause a bottleneck? Well, why don't we just have multiple reducer and train ensembles? Okay, and that's basically our strategy with stochastic gradient descent in a streaming fashion, and then parallelizing out using ensemble techniques. Right? And so on the classifier, on the prediction end, these just become UDFs. Right? So you have the UDF that does the training, it loads in the model, and it does the classification, and you can parallelize this out arbitrarily. Okay, so the very nice thing about this is that it's just Pig. Right? Internally, we've built very nice infrastructure for productionizing Pig scripts. right? And now that machine learning is just yet another pig script that really is a key here, we get all these things for free. We get for free dependency management, scheduling, resource allocation, monitoring, alerting, all the good stuff. Right? And so I think the key takeaway message here is that you have to get the plumbing right in order to get big data mining to scale. Right? Your biggest challenge is these impedance mismatches as you're crossing from one system to another, right? As you're crossing from pig to your machine learning tool, for example. And to the extent that you can eliminate or at least reduce those impedance mismatches, you'll reduce friction and make your data scientists' lives easier. Okay, so I'm going to leave plenty of time for questions, but I think these are the takeaway messages. Right, so the purpose of this is to share with some experiences with you on how to make data scientists' lives a bit easier. And I think the two messages are this. So number one, adding a little bit of structure goes a long way. Now, of course, you have to be careful with this because there's always a balance between getting things right and getting things fast. Right? So let's say, on the front end developing, let's say when you log in JSON, the front end devs love that, right? Because they can just log whatever they want. But what they're doing is they're causing a headache for you downstream so that when a product launches with JSON style logging, you have a difficult time on the back end figuring out if that product actually made things better and moved the needle. Right? So there's always this tension, right? You want to add in some type of structure, but you still want to enable rapid iteration. Okay, so that's takeaway message number one. Takeaway message number two is what I said in the beginning. Big data mining at scale really isn't about data mining per se, fancy algorithms. It's really about getting the plumbing right and reducing the impedance mismatches between the pig or whatever your analytic system is and the tool that does machine learning. All right. Before I take questions, I always like to show this quote. This is one of my favorite quotes these days. Right? So in theory, there's no difference between theory and practice, but in practice, there is. Okay, and I'm happy to take questions. I believe you want to use the mic. Oh, or I can repeat the question. Mm-hmm. So the question is, what algorithm do we use? So we found out that logistic regression works very well for our case. And your other point about having to load all the data in memory, that exactly is what we want to avoid, and that exactly is what stochastic gradient descent allows us to do, right? So the contrast is batch gradient descent. With batch gradient descent, you have to consider all the instances, and that's where you get into the case of dealing with the sloppiness of iterative algorithms that MapReduce, the slowness of that. Right. Other questions? Hmm? Sorry, can you speak up? I can't hear you. Uh-huh. Okay. Okay, so the specific question, just for me repeating, was comparison to a log moving pipeline that Netflix has open source. Is it open source? Okay, so I don't know about that, so I'm not able to make an educated comparison. More questions? Yes? Mm-hmm. Sorry, you'll have to speak up. Maybe it's the lights or anything, but don't be shy, or I'll make you come up to this microphone. Yeah. Uh-huh. Mm-hmm. 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 Okay, yeah, so this is a very good point. This is a very good question. I get that a lot. So what about existing open source libraries that are out there like Mahout, like Mallet, Weka, things like that? And so my response to that is that having Mahout, while Mahout is awesome and great and does lots of things, it doesn't solve the plumbing problem. Right? So the point of the exercise is that, if we wanted to use Mahout, we still would have to answer the question of, well, how do we get our data out of Pig and into Mahout? And then once Mahout runs, how do we get our data out of Mahout and back into Pig for the rest of the workflows, right? So having a machine learning tool is great, but it doesn't solve this problem, the plumbing problem that I talked about. Right? So yes, and we do use Mahout, and our solution is we ended up writing a whole bunch of converters that allow us, Pig storage functions in this case, that allow us to take something and write it out in the vector format that Mahout expects, and then we have a whole other system that does it the other way, that takes the Mahout vectors and then writes it back to our original format. Right? And so the challenge is not in the machine learning algorithms itself, right? I mean, logistic regression with stochastic gradient descent is like 5 lines in Java. Right now, it's probably more because Java is very verbose. So maybe it's like 10 lines in Java. You throw in regularization, so maybe another 20 lines. But it really is not that complicated, right? Yep. Follow-up question? Yes, so the question is, are we making these converters available to community? Yes. It is in the Elephant Bird repository. So Elephant Bird is this system that Twitter developed that does a whole lot of these conversions automatically. Yes, and I believe it's part of that. Any other questions? All right. If there aren't any questions, I guess we're going to all grab coffee. All right, thank you.